Welcome technical developers and data scientists. If you've been building AI applications lately, you already know that Retrieval Augmented Generation, or RAG, is the absolute gold standard for connecting large language models to your enterprise data. But you also know the pain of watching your system pull up completely irrelevant information, hallucinate its answers, or just entirely miss the point. Well, today, we're fixing that. We're talking about contextual RAG. Okay, let's dive into this. Here's our roadmap for this explainer. We'll start with the RAG context conundrum, define what contextual RAG actually is, look at why it changes everything, and finally, we'll map out how to build it and optimize for cost and performance. Section 1. The RAG context conundrum. To understand the solution, we first need to understand the problem. And the root cause of the lost context issue in standard RAG pipelines really comes down to one thing: naive chunking. Let's look at a very realistic scenario. Imagine you have a massive database of SC filings, and your user asks a highly specific query. What was the revenue growth for Acme Corp in Q2 2023? In a standard out-of-the-box RAG system, your pipeline is going to search its vector database for the closest semantic match to those exact words. And it might retrieve an isolated chunk of text that looks exactly like this. The company's revenue grew by 3% over the previous quarter. Think of this as a single puzzle piece sitting on the floor. By itself, it's completely useless. I mean, which company? Which quarter? Because the original document was mechanically sliced into rigid, fixed token windows, say maybe 500 tokens at a time, this chunk has been violently separated from the rest of the picture. This right here is a catastrophic failure of naive RAG. The semantic representation literally loses its critical structural links to the parent document. So, the crucial point is that this mechanical segmentation leads to very specific structural vulnerabilities when you're dealing with enterprise corpora. First up, we have anaphora resolution failure. That's just a fancy way of saying pronouns like it or phrases like this configuration get separated from their original definitions. Next, orphaned comparative evaluations, where performance metrics get completely detached from the entity they're actually measuring. Then there's temporal dislocation, like our Acme Corp example, where relative time markers like the previous quarter lose their absolute anchor dates. And finally, procedural fragment isolation. This one is an absolute late-night debugging nightmare for codebases, where step-by-step operational guides or code blocks are arbitrarily split right down the middle because of some token limit. Section 2. What is contextual RAG? Now that we've seen how naive chunking destroys meaning, we need an architectural bridge to fix it. And this brings us to contextual retrieval. The definition here is absolutely key. It's the process of prepending a chunk-specific explanatory summary generated by an LLM to your raw document segments, and you do this before they ever hit your database index. Instead of embedding isolated chunks, we use the parent document to semantically situate every single piece of text. Basically, we're giving that lost puzzle piece its exact coordinates back. Now, what's really interesting about this slide is the stark visual contrast between a raw, naive chunk on the left and a context-enriched chunk on the right. During the ingestion phase, we pass the entire document and the specific chunk to a cost-efficient LLM, and we ask it to generate a succinct, say 50 to 100-word summary. The resulting text on the right now explicitly contains Acme Corp and Q2 2023. So when you embed this augmented chunk, your vector database captures that deep contextual information, perfectly aligning it with a global document structure. Section 3. Why it changes everything. It's one thing to say this sounds smart in theory, but let's look at the hard data on why this architecture is rapidly becoming mandatory for modern AI apps. Let's walk through these Anthropic benchmarks. They measure the top 20 retrieval failure rate across diverse datasets, like huge code bases and complex scientific papers. Bar 1 is your baseline naive RAG. It fails to retrieve the right chunk in the top 20 results 5.7% of the time. By simply adding contextual embeddings, that's bar 2, that failure rate drops to 3.7%. But look what happens when you implement the full pipeline, adding contextual BM25 and a re-ranking step. The failure rate plummets to just 1.9%. That represents a staggering 67% reduction in overall retrieval failures compared to traditional methods. By preserving the semantic integrity of your data right at the ingestion phase, you're virtually eliminating the hallucinations and dead ends that constantly frustrate your end users. Section 4. How to build it. Let's move to and see how this builds out into a practical, production-ready engineering pipeline. The execution phase follows a really straightforward 4-step blueprint. First, you chunk the parent document. Second, you generate the context for each chunk using an LLM and prepend it to the text. Third, you index those augmented chunks using a hybrid search approach. And fourth, you re-rank the retrieved results before passing them to your generation model. We've already covered the first two steps, but step 3, hybrid search, is where the magic really gets locked in. Now, to do hybrid search correctly, you really need to understand BM25. While dense vector embeddings are amazing at capturing abstract semantic meaning, they can easily miss exact token-dependent technical queries. BM25 is a probabilistic ranking function that uses lexical matching. It looks for precise word or phrase matches. So, if a user searches for an exact error code like TS299, semantic search might just return general documents about system errors. But BM25, it will find that exact string. So the trick is, you run both searches in parallel, a semantic vector search and a sparse BM25 keyword search. But how do you combine those results? You use reciprocal rank fusion, or RRF. RRF is basically the mathematical glue that intelligently merges and deduplicates the candidate sets from both search paths and ensures you get the absolute best of both worlds. But wait, you don't just weigh them equally. Production evaluations, particularly on really complex tasks like code-based searches, show that an 80-20 split is optimal. You assign 80% of the weight to your dense semantic search to capture that paraphrased intent, and 20% to your sparse BM25 search to act as an anchor for exact, domain-specific terminology. Once retrieved, you pass this combined list to a cross-encoder re-ranker model. This scores the exact query document relevance and filters it down to the absolute best top 20 chunks for your LLM. Section 5, Optimizing Cost and Performance. Okay, I know exactly what every developer listening is thinking right now. This sounds incredibly expensive. And you're right to be concerned. As this quote highlights, passing an entire parent document alongside every single segment to an LLM scales your input token consumption quadratically during the ingestion phase. Think about it. If you have a 10,000 token document split into 20 chunks, you're processing 200,000 input tokens just to generate the context. Without mitigation, that compute cost is a massive barrier to enterprise adoption. But here is the good news. You can achieve up to 90% cost savings on ingestion by utilizing a feature called prompt caching. And this brilliantly illustrates exactly how it works. When you process your chunks sequentially, the LLM provider loads the parent document into memory on the very first API call. For every subsequent chunk processed within the cache window, which is typically about 5 minutes, the model reads the parent document directly from memory rather than recalculating it. Processing 737 chunks from a codebase without caching cost about $9.20, but with caching, you hit over a 61% read rate, dropping the total cost to just $2.85. You get all the precision of contextual retrieval for a fraction of the API cost. It's a total game changer. To give you a highly actionable blueprint, here's a quick summary of the recommended production tech stack based on the benchmarks from our sources. For context generation, you want to use models with strong prompt caching, like Claude 3.5 Sonnet, or small, incredibly fast models like Llama 3 2B. For embeddings, Voyage AI and Gemini Text Embedding 004 show top-tier performance. For your vector database, Elasticsearch is fantastic because it handles both hybrid KNN vector search and BM25 natively. And finally, use Cohere Re-Rank v4 for that final precision filtering pass. So as you look at the architecture you're building or maintaining today, I want to leave you with this question. Are your AI's answers actually grounded in context? Or are they just floating in isolated chunks? By shifting to contextual RAG, utilizing hybrid search, and leveraging prompt caching, you can eliminate the lost context problem entirely and build an incredibly robust, enterprise-grade retrieval pipeline. Thank you so much for joining me on this explainer, and happy building!